Alright, so a furnace shaped like a long equilateral triangular duct. So something like this, and it's really, really long. And each side is 2 meter, 2 meter, 2 meter, 2 meter. Right? The heat is supplied from the base surface. So how he's supplying that heat from the base? Maybe he has electric heater, or maybe he has flames underneath, but he's supplying heat, and the heat is 800 watt per meter square. All right. I never really. He didn't tell us the depths of the thing. It's infinitely long, so maybe we should consider 1 meter. Right. We'll just solve it per unit surface area. Right. So you can imagine. So here is surface 1. So we will just assume A1 equal 1 meter square. So either use unit depths, and therefore the area at surface 1 would be 2 by 1, or you just assume that I will use unit area at the base. And therefore this would be not 100 watt per meter square, it will be 800 watt. Right? Not 800 watt per meter square. It will really just be 800 watts. Alright, anyway, so that Q that's delivered from the base, where will it go? The electric heater or the furnace or the flames or whatever supplying those 800 watt, where would those 800 watt go? It will probably go to the other guys, right? There is no other way. What I'm trying to say is that the surface at the bottom cannot store them. If you give him at steady state, if this is an engineering furnace, it's not a furnace that's planning to burn and melt from us, but engineering furnace that will work for hours and hours and hours. It should be steady state. Q delivered should be the Q basically radiated back to the other surfaces. Okay, very good. And so he said that the side surfaces are whose emissivity is 0.4. So here is, so this is called 2. And should we actually call this 3?
No.
Or should we call it 2 also?
It's 2 because it's symmetrical ladder triangle.
2 since they're the same.
Symmetry.
They are the same, the symmetry. And also in the hint, actually there was a hint saying this geometry can be treated as 2 surface enclosure. He's basically telling you, because of the symmetry, it's like just like basically base and kind of roof. And that's similar to the, remember, what was your name again? Robert got free homework last time for this, because he realized that all those 4 surfaces, they are exactly the symmetry. They have exactly the same F, 1 to 2 and F1 to 3 and F1 to 4. So really we can just treat all those surfaces over here in this place as one surface sitting on top of the floor. Right? So the same thing over here. So there is no point calling it 2 and 3. Let's actually just call it 2 and 2. Right? And so given epsilon 2 was 0.4 and it's maintained at 600 Kelvin, and neglecting the end effect, determine the temperature of the base surface. So required is T1, and actually epsilon 1 was also given, and epsilon 1 was 0.8. Solution. So the thermal resistance that's equivalent to something like this is just 2 body, T1 and T2, or surface 1 and surface 2. Right? And we said surface 1, he wouldn't radiate like a black body radiation. He will not radiate with sigma T1 to power 4 because of the surface. Right? So he will radiate J1. And how much is the surface resistance to radiation? 1 minus epsilon 1 over area 1 epsilon 1. And the same thing for surface 2. He will not radiate like a black body. He will not, because he's not black body. He's not, doesn't have epsilon equal 1. If he had epsilon equal 1, he will just radiate with sigma t 2 to power 4. But because of his 1 minus epsilon 2 over area 2 epsilon 2, he will radiate J2. Okay, and so what is the resistance between J1 and J2, or the space resistance to radiation, or the geometry? I like to call it actually geometry resistance rather than 1 over which A and which F.
F1 to 2.
So then it's A1, F1, 2.
Right.
And someone else could have said A2, F2, 1. Probably F1, 2 is better because F1, 2 is
That's the right direction.
excellent.
Right direction.
Huh?
That's the right direction.
He's going from 1 to 2. And we know A1.
So are you saying F12 is 1 because Mallory? Are you saying F12 is 1 because it's moving in that direction? That's not the reason why F12 is 1.
Because that's all of the transfer. All
Right.
of it from
Because
one
the
to
what leave 1 is have two places to go, right? In this world where the world is only 1 and 2, there is only F11 plus F12. If there was a third surface, it would have been F11 plus F12 plus F13 would be equal to 1. But in this world, whatever leave 1 sorry, can either go to 1 or can go to 2. And of course F11 is 0 because,
Shouldn't you have two
Can't go
F1
this
twos?
say that again.
Shouldn't you have a coefficient of 2 for the F1 2?
No, we're treating it as one group.
It's treated as one whole piece.
Right, so this surface 2 and surface 2, this is just one surface. It just looks like this. It's bent into, and actually surface 2 can also even be not connected to itself. Let's imagine we have a roof like the example we solved before. If we have a roof and 2 and 2 are identical, same epsilon, same temperature, I can still look at those two walls that away from each other, and I would think this is surface 2. Right? So surface 2 does not have to be connected to itself to start with, as long as it's the same temperature and same epsilon. All right? Let alone that if you think that surface 2 need to always be a flat surface, no, it does not have to be a flat surface. It can be half a sphere. You know, this problem, we can solve like, say, if it's like a disk and then half a sphere on top of it. And here is 1 and here is 2. How much is F12? 1, because everything leaving 1 will have to go to 2. Why? Again, because F11 is 0. Why F11 is 0?
Why it cannot go to this cell?
Because he cannot see itself. He cannot radiate to itself. He's not concave. Right? A flat surface or a convex surface cannot see itself. Cannot radiate to itself. Alright? So because of all this, F12 is 1, right? And so that's really convenient. Rather than saying, notice that F21, how much is F21? No?
Isn't it one because the areas are the same?
Let's think. F21 is,
0.5.
what's F21? That's the radiation leaving 2 and going to 1, right? So F22 plus F21 is 1, right? Of course. Everything leaving 2 either go to 1 or go to 2. There is no other place in this world.
0.5.
There is, by the way, the 2 ends, but he said in neglect end effect. He's assuming this thing is very, very tall, that they don't really care about the ends. It's really far away and very tiny compared to the whole surface area. So radiation leaving 2 will have to go to 1 or go to 2. And so does anyone suggest here that F22 is 0?
No, because they can see each other.
Right, so why then you think F21 is 1? So F21 is not 1 and it's not 0. F21 is something, but it's not 0 and it's not 1. And the way to get it,
2/3.
how? Well, I don't have to guess really. All I have to do is open the table, open the chart. There's a chart for two surfaces with an angle between them. and you can get that F22. And from that you can get F21. We don't care because we have F12. That's all we need to solve this problem. We don't care, right? James, you had a question? Okay, so we don't care about F21 really. If we can solve it from F12, correct? Again, this resistance can be either A1 F12 or A2 F21. It's exactly the same number. All right. So he's asking about T1, and he gave us the Q, right? So that Q dot delivered to 1 will have to be Q dot 1, 2. Everything delivered to 1 at steady state need to be sent to 2, because the surface will not be able to store it at a steady state. So I know Q dot 1, 2. I know T2. I know all the resistance, and I would like to get T1. Can anyone help me? Calculate T1. How can I do that?
Write three equations and find your J's.
Those three equations were when we have three nodes, J1, J2, and J3. Now I only have J1 and J2.
Could you just take,
Are you talking to the three equations that we did last example in the last class? Are those the three equations when?
Write three equations.
You are talking about
Yeah, from that guy.
like from here
this
to
guy,
here to
and then-
here, right. Or we can just write it as one equation. From here to here.
sigma T, sigma T over the resistance?
Right. Let me write it. So Q dot 1, 2 is. I thought that you were talking about the three equations that we wrote last time between J1 and J2 and J3. Remember this example last class? So now we would write just sigma T1 to power 4 minus sigma T2 to power 4 divided over
All the resistance.
all the resistance. 1 minus epsilon 1 over area 1, epsilon 1. We can, that's excellent. So we can actually cancel the A's later or take them out because,
Are they the same?
not really.
And then A2 is the same?
You're getting 800 watts.
Area 1 and area 2, what do you think area 2 relation to area 1?
Twice.
Twice as much. So area 2 is twice area 1. So if we assume area 1 to be 1, then area 2 will end up being 2. If you said, let me use, I don't want to assume unit area, I will just assume unit depths. That makes sense to my head, you know. Let's just have unit depths. So area 1 will end up being, if I assume unit depths, then area 1 would be,
Or no, 4.
if I assume unit depths, he gave us this cross section and we are assuming unit depths. Assume this is 1. Then area 1 is 2. 2 times 1, that's a square rectangle. 2 times 1, that's 1. And area 2 would be, how much? Area 2? 4. Twice as much. Right? Okay, I think it's easier to just assume area 1 is 1 and therefore area 2 is, right. So basically I'm solving the problem per unit, per 0.5 meter depth. Why I think it's easier this way? Not because I like the number 1, but then because the Q dot become 800. I don't have to modify the Q dot. So that makes sense to me. So anyway, so 1 over area 1 plus 1 minus epsilon 2, area 2 epsilon 2. Alright? So you know the Q dot, we said it's 800. Now it's 800 watt. Not per meter square, it's 800 watt because the area is 1 meter square. Right? And we know sigma T1, we know sigma T2. And we are, the only thing that's unknown in this thing is T1. And so you get T1 out of it. Alright? Question about this?
Missing a 2, but it's more.
What am I missing?
Never mind.
Let's just, your equation doesn't have the 1 over it.
The F12? Right, well, I intentionally remove it because it's 1. I wanted to remove it. Right? And of course, we said sigma, that's Stephen Boltzmann constant, that's the 5.6, 5.67 10 to minus 8. Right? You will never forget that constant, 5, 6, 7, 8. You may forget the minus, but that's a big deal, of course.